Utility-scale solar projects demand vast stretches of land, a resource that is increasingly scarce and expensive to acquire. To bypass these territorial constraints, energy developers are turning to a massive, mostly untapped resource: open water. In India, this shift is driven by a massive central initiative. The PM Sarovar Yojana targets the construction of 5,000 megawatts of new solar capacity, specifically engineered to sit directly on top of existing reservoirs and industrial ponds. The core physics of these arrays are exactly the same as their land-based counterparts. A photon travels from the sun, strikes the silicon cell, and excites the electrons inside to generate a steady flow of direct current electricity. But operating on water introduces a distinct physical advantage. The reservoir acts as a massive natural heat sink, continuously providing evaporative cooling to the underside of the panels. This constant thermal regulation drops the operating temperature of the modules by 2 to 8 degrees Celsius, effectively counteracting the heat degradation that normally throttles silicon cell performance. The result is a 5 to 15% net energy premium. By simply moving the same technology onto water, plants generate significantly more power from the exact same amount of sunlight. Deploying this hardware means building on sprawling reservoirs and deep water dams. Supporting thousands of heavy solar modules over these depths requires a specialized, highly buoyant architecture. Engineers rely on high-density polyethylene, or HDPE, to create the primary building blocks of the plant. These are hollow, heavily UV-resistant pontoons designed to survive decades of continuous aquatic exposure. Instead of one massive barge, the system uses a modular, interlocking design. Thousands of these individual pontoons snap together, creating a flexible base that supports rigid aluminum or composite mounting frames. The buoyancy calculations are strictly regulated. Even under the maximum static weight of the solar equipment and the dynamic forces of the water, the pontoons must maintain a minimum freeboard of 150 millimeters above the waterline. By distributing the load across this interconnected HDPE grid, the array acts as a single structural island, buoyant enough to float, but rigid enough to carry industrial-grade power generation equipment. Once the platform is assembled, it faces severe environmental threats. During storm events, the massive surface area of the panels catches extreme static wind loads, while the water below batters the pontoons with dynamic wave action. To keep the platform from drifting, engineers secure it to the reservoir bed using heavy anchoring systems. Depending on the soil conditions, they deploy either massive gravity anchors that hold by sheer weight or driven pile anchors drilled deep into the mud. These anchors must account for the most extreme hydrological variable in Indian reservoirs, the seasonal drawdown. Between the monsoon and the dry season, water depths can swing by 10 to 20 meters. If the plant is tied down with fixed-length cables, this variation would destroy it. The solution is a catenary mooring system. The mooring lines are designed with specific lengths of extra slack, forming a curve that naturally pays out or takes in as the water level rises and falls. The tension tolerances are incredibly tight. If the lines are tensioned too tightly during a low water period, the interlocking structural pins on the floats will snap. If there is too much slack, the platform drifts out of its optimal solar azimuth, bleeding generation efficiency. To absorb these continuous kinetic forces, the physical mooring lines rely on high-tensile industrial materials, utilizing combinations of synthetic fiber ropes, polyester, and heavy steel chains. This precision mooring engineering is the vital connective tissue of the entire operation. It is the only thing preventing a multi-million-dollar power plant from tearing itself apart in open water. Up on the platform, developers are moving away from standard solar panels. Instead, they increasingly specify bifacial monocrystalline modules, which are coated in photovoltaic material and active on the rear side as well as the front. Because water naturally reflects sunlight, these bifacial panels can capture the surface albedo. Bouncing that light into the rear of the module generates an additional 3 to 6% energy boost. The direct current electricity generated by these panels must immediately be protected from the wet environment. The power flows into heavy-duty IP68-rated waterproof flexible cables, engineered to withstand both harsh UV rays and continuous wave motion. These cable strings route the electricity into weather-resistant combiner boxes. From there, the consolidated power travels to massive floating inverter stations, 60-ton platforms constructed from ultra-light ferro-cement. Inside these floating stations, the inverters convert the DC electricity into alternating current. The power is then stepped up in voltage by floating transformers. Crucially, these transformers are filled with natural ester oils, entirely eliminating the risk of toxic chemical spills in the local water supply. To move this high-voltage AC power to the mainland grid, the final connection utilizes a flexible catenary cable loop. This loop rides on specialized floats, self-adjusting to bridge the physical gap between the moving water and the solid shoreline. This unbroken, heavily armored electrical highway maintains absolute isolation from the surrounding water, safely delivering grid-scale power from an actively shifting platform. Even with secure moorings and waterproofed cables, the marine environment wages a constant war of attrition against the hardware. The plant faces invisible, microscopic threats: humidity-induced corrosion on the metal frames, potential-induced degradation within the cells, and the steady UV breakdown of the structural plastics. Below the waterline, aquatic organisms attach to the pontoons, a process known as biofouling that adds massive drag and weight to the platform. Above the water, bird droppings create aggressive, localized shading on the glass. That localized shading blocks current flow. The trapped energy converts into severe heat, creating electrical hotspots that can trigger catastrophic bypass diode failures directly within the silicon array. To combat these hazards, maintenance teams rely on autonomous drones. Equipped with thermal imaging, these drones safely scan the sprawling arrays from the air, instantly identifying heat anomalies before they cause permanent damage. Down on the arrays, specialized cleaning robots glide smoothly across the module surfaces. They wipe away dust and biological debris, completing the necessary cleaning cycles without ever risking human operators on the wet, high-voltage platforms. Hitting a 25-year operational lifespan on water is not a passive existence. It requires constant, high-tech vigilance against an environment actively trying to consume the infrastructure. Integrating interlocking HDPE grids, 60-ton floating ferro-cement inverters, and highly dynamic self-adjusting moorings into a single cohesive megastructure is a massive feat of engineering, and it is highly lucrative. As these gigawatt-scale floating projects multiply across the globe, the race to own the underlying intellectual property is accelerating rapidly. Which leaves us with a critical question for the future of energy. Who exactly is inventing these foundational technologies, and which nations are currently leading the global floating solar patent race?